Welcome back. We're starting part 4 of our chapter 10 on the persistent data layer. In this chapter, we're going to continue our discussions and go over how we take changes that happen in game and push those changes to the persistent data layer so that should the application crash, you have all of your items still when you come back in, or if you log off normally and come back later, log back in, that we get you back your items. So the important aspect here is that we are pushing our changes to the database so that when a player comes back, all their items are available for them to use. So first, let's talk about a couple of the changes since our last video. As we've continued to flesh out our solution, the first thing is we switched. In prior videos, we were using what we were calling the persistent player state component, and we were attaching that to the player state so that we could pass the data back and forth through the player state. We've actually now shifted to creating a child class of the Lyra inventory manager, which is by default attached to the player controller. So in earlier videos, we were talking about the persistent player state component and attaching that to the player state. Now we're going to be attaching our own custom Lyra inventory manager, which is a child of the standard Lyra inventory manager, to the player controller. In order to make that work, there was a couple of decisions we had to make in the base Lyra project. So the base Lyra project, I believe in Shooter Core, loads the Lyra inventory manager onto all player controllers. And because of that, it means that no matter what your game experience is, you're going to have the Lyra inventory manager. Well, we wanted to have different inventory managers for different experiences, and therefore having the plugin's data asset auto load the inventory manager on every player controller wasn't going to work for us. So in order to do that, what we did is we removed the component add in the plugin and then added it to each of the Lyra experiences. So each Lyra experience, the elimination and the capture point, now have the Lyra inventory manager added to them, so that we could then use our own Lyra inventory manager on our experience, which I'll show you when we jump into the application. For quality of life, we created a save username and password. We just got tired of typing the test username and password over and over again. And so if you wait until the end of this video, we'll explain how we did that, show you that at the end. It's more of a quality of life. It has nothing to do with the persistent layer. And then we added the Lyra inventory item definition to the asset manager. This is something that we may or may not finalize our design on, but by adding the Lyra inventory item definition as a primary asset, we can be assured that packaging of the project will pick up all of our item definitions. Since item definitions may not be in a level or a map, they may not be referenced exclusively in hard links, we thought it's safer to make sure that packaging picked up all those item definitions when packaging the project. And then we had to go into the Lyra source code and add the module name, the Lyra game API, to both the Lyra inventory item definition and Lyra inventory item instance classes, so that when we were compiling and linking our code, we would pick up those two definitions. So without a module name in the class definition, the Unreal editor packaging or header tool won't create the necessary linkages for us, and you end up with linking errors. So if you're getting link 2019, it is likely that you are referencing a class that does not have a dash API in front of its class definition. So those are the changes that we made going into this video, and we'll cover them as we walk through the solution. Next, let's talk about some of the key design decisions around when and how we push data to the database layer. So the first question you have to ask yourself is, how often do you need to push that data to the database layer? You can do it every time you change one of the items. So use an item, pick up an item, craft an item. Basically, the more frequently you are sending information to the database, the less likely something is going to get lost for your players and cause player frustration should a server go down or some scenario such as that. Next to that, we thought, okay, well, what about just important changes? So maybe some minor changes aren't necessary, like putting something in storage versus having it in the player's inventory. If that crashed, happened, and it was still in your inventory, you wouldn't be as upset as if an item that you just got suddenly disappeared. Next, we thought about periodic timers, which might be a bit more performant than every time you pick up an item, but it could be very prone to inconsistencies. If crashes are occurring, timers are running, you're just going to get into a lot of timing issues that might be difficult to debug later down the road. And then the fourth one we thought about is, okay, at the end of a match or the exiting of the game, right? So when you hit the quit button or the match timer expires, would that be an opportunity to save to the database? And that one probably is the most crash prone. So if you disconnect from a match, you don't want to lose all the stuff that you've earned in that match. And so all of those, we ended up with every change. We think it's going to be performant enough. We're going to load the system with a couple of hundred items and test that. But for now, we're doing an every change model so that nothing gets lost in the eventuality of a crash. The next major question we had to answer is, okay, where do we best insert or inject this persistent call into the way our data is flowing? And luckily for us, in our earlier design, we forced all of our updates to be inside our gameplay abilities. And so if you watch the earlier chapters, no matter what we were doing in the UI layer or in the world, it all ended up calling a gameplay ability, which on the server would perform those actions on the inventory manager. And so it became very easy for us to say that the best place for us to inject the persistence layer would be inside the gameplay abilities themselves. Then we thought about how to do that. And since we wanted to adhere to a write code once and just have it be kind of easy to execute, the logical conclusion is to stick it on the on-end ability node. And we'll show you how we did that so that every time an ability completes, it will automatically persist all of that data back to the database. And then one last thing to mention here before we move on is we're still working on a little bit of an issue, which is why this video took a little longer to get out. How to add the item instance, primarily on entering a session. So when you think about it, when you enter a session, you're going to go ask the database for all the inventory that I had, and then you're going to basically give all that inventory back to the player. And there's a couple of different ways we can do that. We're still working through some issues and some bugs, whether we use the asset manager and look up the item definition in the asset manager and then spawn that in, or whether we do some variant of load static object or load static class. We're still playing with some of that. So that particular piece of the solution is not yet ready. We will do another video when that is ready to show you the whole fully functioning system. All right, so we have several abilities that change the state of our inventory manager. So these are just listed here on the screen. When we slot an ability into the active slot, we are storing that in the inventory system. When we get a new skill point, we're storing that as a currency in the inventory system. When we enable or add a skill or remove a skill, those are tracked in the inventory system. Our crafting is done in the inventory system. Anything we pick up in the world or farm from a node, and then any of the actions we do in the core inventory chapter of swapping things in and out of storage, combining stacks, etc. So each of these abilities needed to be enhanced in such a way that they would call the request to persist the inventory. All right. So let's take a look. Let's look at it in action. Why don't we do that first? And I don't have the editor up and running. Okay. So I'm going to launch that. So as this is loading up, what we'll do is basically launch in, as we do for our user authentication layer. We'll drop into a zone, and I will show you the result of persisting the data back to the database. Okay, so the first thing we're going to do is move to our login front end. And let's launch from here. And you'll notice that my email address and password are already filled in. This was the quality of life change that we were talking about. It's just a lot easier than having to log in all the time. Start a new match. And we'll launch our persistent world. So at this point, it's attaching the modified inventory manager to the player controller. And then we're launched into the experience with our modified inventory controller. So the first thing I'm going to do is go over here and pick up a single log. All right. With that log in my character, let's go to our database server. So this is our database. And these are our database records. And this is the character we're working on. So we're going to pull the current state of the custom data field. And for our purposes, we're just going to paste it into the notepad. So I have my pistol, my skill points, my skills, and my one wood log. So here's the data that I just picked up, the one wood log. If let's pick up second wood log and open the storage bin, take our two logs, put them in storage. Now let's go back to the database, refresh the database, copy that string. Sorry, there's no easier way to show you this. paste in the new string. You'll see that I now have 2 stacks of logs, and they are in fact in storage. All right, let's do a couple of more things to, we'll leave our logs in storage. We'll collect 3 rocks from a node. We'll go over here, we'll pick up our crafting recipe. We'll pick up our material. We'll interact with the crafting station. And we'll make a necklace. Okay, let's make another necklace so we trying to get a crit. Okay, 2 regular necklaces. Okay, come on. All right, enough of that. All right, back to the database. Refresh the data structures. Copy this value. Paste in our new structures. So now we see that we have a lot more things. We have our skills. We have our 2 logs that are in storage. We have our 3 metal ores that we picked from the node. We have the recipes that we picked up off the table. And we have the necklaces, the 4 necklaces that we crafted. Let's go spend some skill points. So if we pull up our player window and we spend a skill point, spend a skill point, unlock an ability, go to the abilities, drag that ability into our slot. And now let's go look at our database again. So before I refresh this, I started with 5 skill points, and then I spent, I think, 3 of them, maybe 4, I think 3. Skill points. I have 1 skill point left. I activated this skill. I have not activated that. I activated this skill. I activated that skill. These are our resources and recipes. And here is burst. That is stored in the ability slot 01. This might be a bug. I have to think about why those 2 are there. But you see that the ability is stored. You saw the, so basically all of our functions are persisting to the database. Let's look at the changes that were necessary to our gameplay abilities in order to trigger the persistent inventory stores. Actually, let me launch this in the background. So each of our gameplay abilities that we had worked on in previous chapters has a parent class associated with it. So all of the inventory ones end up going to this inventory actions base, which had a variety of helper functions defined in it and was originally inheriting from the Lyra gameplay ability. So we went ahead and created a new child of the Lyra gameplay ability called Lyra gameplay ability persist. And what that basically does is that any gameplay ability that inherits from the Lyra gameplay ability persistent is going to automatically save the inventory file upon end ability. So when this ability ends, it will automatically trigger. So some other examples, like when we do crafting. So when we perform crafting, these are the steps in the crafting flow. But again, by making the parent Lyra gameplay ability persistent, then when the ability ends, the system will automatically write the data to the database. So all of the classes that end up doing that, so these ones do not because they don't change any of the data. The ability, the drop ability slot does. So it should inherit from a Lyra gameplay ability persistent. So all of these that do something that changes the inventory, we've changed their parent from the Lyra gameplay ability to the new Lyra gameplay ability persistent. And if we go into the C++ for that, here's our Lyra gameplay ability persistent. It is a child of the Lyra gameplay ability. And it has one function called persist inventory. And it does an override of the end ability. So this override is basically being called anytime the ability ends. And that end ability will first persist, which is our function above, the inventory, and then end the ability normally. So it calls the parent class of end ability. When it does call persist inventory, we get the player controller, we get the component actor for our inventory management component. So we get that actor component, we cast it to our, get access to our functions. We check that it's okay. If it's okay, we do our update persist inventory, and that's it. So just by adding this parent class in the hierarchy, every time a persistent ability gets called, it will automatically trigger this function persist inventory, which will in turn call the inventory manager and update persistent inventory. That update persist inventory will loop through all inventory items, and it will basically create the struct by pulling the information from the stat tags. So if we have a stat tag count, we'll go ahead and get that count. Otherwise, we'll assume 0. If we have the in storage tag, we'll get that count. Otherwise, we'll assume 0. If it's slotted, right, we'll get the slot tag, convert it to a string, and store it in the working structure, and then add that inventory to our array, which is building. By the time we get through each of the inventory items, we will have an array of packaged inventory, which will contain all of the data elements that we want to persist. We then use our JSON conversion. We convert that array into a string. Then we call our add or update custom character data for our currently selected character. And using our resulting JSON string, which was this packaged inventory, we send that off to the database server. And it's kind of fire and forget. We don't have to worry about it. But basically, if we wanted to keep following the flow, that routine, add or update custom character data, will formulate a web call with the character name, custom field, custom value. It'll take our add or update custom data set and add post parameters to it. So it's formatting more information. And then we'll call the OWS2 post request in the character persist API, passing this API definition, the post parameters that it just made here, and it will assign this callback function here. So our post parameters include the custom value that we passed in. Right here is field value. The field name, which we passed in, the character name, which we passed in. Pass that all to the API. The API comes back, and we simply have either a success or failure. So that's how, when we use the ability, because we've set the parent, the on ability end fires, that calls persist, which then in turn grabs the inventory manager, loops through all of the inventory items, creates a JSON string of that, and sends it to the database server. Now let's take a quick look at what happens on startup when I enter a session where this inventory manager is attached to that player controller. So if you remember, our game experience will attach this inventory manager to the player controller. As we enter a session, the player controller spins up. It spins up its components. This component will receive a begin play event. So the inventory component will receive begin play. And we're going to go ahead and cache the player controller just for convenience sake. It's easier than casting it over and over and over again. We'll check if we are the owning controller and we're locally controlled, or if the cached owning controller is locally controlled, then we can get our own game instance, and we can attempt to server connect. This is complicated. So because I'm locally controlled, I am the inventory manager on the client who is directly related to an inventory manager on the server. And therefore, because I'm part of the player controller, I can make RPC server calls to the server. So the local copy of this component will pick up its Lyra game instance where we store the client session GUID and the selected character GUID, and it will attempt to call this server connect to persistence, passing the client session and passing the selected character. So this function is defined gotta find it. Here it is. So the function is defined as execute on server reliably. And so a client who has authority over this component may call this, but the code itself will run on the server. So here's the call. We pass in a constant string for the session GUID and a constant string for the selected character. Because we're using the server in the U function, it means we have to append underscore implementation, and we have to have an underscore validate. So our void and Boolean versions of the implementation itself and the validate. This would allow us to do any further validations. In this case, we're just going to pass back true. We take the passed in user and characters, store them in our active on the server, and then we request from the database. So we're now on the server. This function is happening on the server. We now do a request for the persistent inventory, which calls the API, get custom character data, with our selected character. That formulates our JSON, calls the appropriate API, and hands it a callback function. So when the API builds its JSON string, it's going to pass it back to this function, which is here. So we receive control back in the callback. We check if we were successful. If we're successful, we're going to send the JSON object to our inventory received function. So here's our inventory receive function. We convert that JSON object to our uStruct, and then basically start to process our structs and determining things like, all right, if the stack count is greater than 1, go ahead and set up the stack count in our inventory. If the storage tag isn't 0, go ahead and change the storage tag. Same thing with the active skill active tag. So these are all basically unpacking the result of the JSON that came back through the API that we converted to a structure that we then can process and create each copy of our inventory in the inventory manager. So in conclusion, one last summary of this chapter. We have the player controller that is added a child version of the Lyra inventory manager. In order to accomplish that, we had to move the standard Lyra inventory manager from the game feature data asset into the game experiences for the standard elimination and control point examples, which allowed us to add the child version in our own game experience. That allows us to communicate back and forth with our game instance, which has our session ID and character, which are set when we log in. That child Lyra inventory manager uses the server function to pass that data from the game instance into its own server version of the inventory manager. At begin play on startup, that inventory manager will request the inventory from the database. It uses a web API and JSON formats to extract the data from the database and populate the inventory manager in the startup state. Then as we are executing abilities in game, the Lyra gameplay ability class has been subclassed to our Lyra gameplay ability with persistence. Any actions that use the persistent version of this will automatically trigger on end ability a call to persist the inventory, which will use the web API and the JSON to push the new data back to the server. So we only fetch the data once at the beginning of a session. There could be some use cases where you may want to fetch it again, but right now at the beginning of the session, you establish it. As you do things throughout the game, end ability pushes data back to the database. And that should be all we need to keep our system persistent. We'll do one more video after this once we've finalized and tested it a bit more to run the system from front to back. But that should give you a good understanding of how to persist data throughout the game into a database layer using APIs. So stay tuned and we'll talk about the login window next. All right, as we said at the beginning of the video, that once we got through the persistence data content, we'd come back and share how we created the save login information in the login window. So let's go ahead and take a look at that. So we're going to quit. And all right, so the information is stored in your in a save game format, which by default saves into the saved folder of your hierarchy. So the actual data store is this very simple class, which you just need to do a blueprint class and give it a base class of save game. So if you use this as the base class, I called ours save game login information. And in that save game, we have the 3 fields we want to save: the email address, the password, and the save info. And 2 simple functions, one to store it, which just looks like this, and one to get it, which just looks like that. So the save game itself, extremely simple. It's simply a data structure of which information you want to save. Now, there's also a way to save using the parameters on your variables to save games. You can use this flag here under the advanced settings. So under advanced save game, you could basically serialize and save information that way. This way is a much simpler and easier, less complicated approach. So we have our save game that is going to store that information. And then in the login widget, which is where all of our code resides, first we added the new field and checkbox to save our information. In the event graph, let's close all but this one. So in the event graph, upon activate, we have a function called retrieve save info. So we do that to determine should we get the save info from the save game and populate the fields. We do the rest of our normal startup activities. And then upon button click, we basically continue our normal login session information. We broadcast. Sorry, my mistake. On deactivate. So when the window is torn down, we save the information before getting rid of the window. So on activate, we get it from the save game. On deactivate, we set it to the save game. So let's take a look at those 2 functions. For the saving, we first check if our save game exists. If it's not, it means it's the first time. So we're going to go ahead and create a save game on disk and then basically initialize it to this slot and this user index. We then turn around and load it, because if it did exist on the true path, we would be loading it. So this just says, look, if it doesn't exist, create it first. If it did exist, just go ahead and load it. And again, we're using the login information as our common denominator. Once we get the save game, we have to cast it to our save game asset. And then we check if the screen check mark is checked. So if the check mark is checked on the screen, then we're going to follow the true path. If you unchecked it, we have to sort of blank out anything that might have already been saved. So in the use case where I had been saving, but I turned the check mark off, we'll follow this false path, and we'll simply store blanks over top of any save game information. In the case where we are saving, we'll get our, this is just a helper function to get the values from the strings. So all that does is pull the text values off the fields, converts them to strings, and passes them back. We'll get our email and password. We'll encrypt the strings because it's important not to store the password unencrypted on disk. So we're going to use the encryption method to encrypt those. And then we pass those encrypted strings into the store data function of the save game, and then save to slot. So the only other thing to look into is these encryptions. So we're using our encrypt with AES, which is a function we have in our Lyra game instance, which takes a string and a private key. So in this case, we just created a random GUID as our key. And so you need to know this key in order to decrypt the string. So on the decrypt, we use the exact same key. So it's important that both of those keys are identical, or else it won't be able to decrypt the encrypted version. And they're just the opposite. The decrypt takes the encrypted string in, uses the key, and passes back the plain string. Where the encrypted takes the plain string, encrypts it, and passes back the encrypted string. I think I was here. So yeah, so on storing information, we're encrypting it. And then when we retrieve the information, so here's our retrieval process. Check if it exists. If it does exist, load it. Check if we have the save game flag on. If it is, go get the values that are encrypted and decrypt them and put them in the fields on the display. And then based on whether or not we are checked or unchecked, we simply set the enum for the save info checked or unchecked. So that's basically it. Two nodes called retrieve and save, called on activate and deactivate. Two helper functions in the encrypt and decrypt, or three helper functions and the get value to strings. And so when we run that on activate, the value is retrieved from the save game. And the save game is stored in your saved folders saved game. So under save folders, you have save games, and then you have whatever you named your save game. So in this case, it's this login. And if I open it, you'll see that the actual username and password have been encrypted. So you can kind of feel that the email address is somewhere around here, and then the password is somewhere around here, but they're both encrypted in the file. So if I wanted to, so for example, if I quit, if I delete that save game file, so the save game no longer exists. There's nothing for me to retrieve. I can type in my password for the first time, ask it to save, and it will recreate the save game asset on disk. All right, hopefully that's helpful for you.